welcome to CEC lectures. Myself Dr. Preeti Chagwani. I am Associate Professor, Department of Computer Science, Hyderabad College, University of Delhi. So we are presently going through our course of advanced data structures and algorithms. So in this we are currently looking into the topic of hashing, and let me give you a quick recap that in hashing we have already understood what hashing is, what are different hash functions, and then we started with the collision resolution techniques. Within the collision resolution techniques, we have looked into linear probing and quadratic probing also. Now, today's agenda is about chaining, which is kind of another we can say collision resolution technique. So, basically whenever there is a collision between two keys, and two keys are actually competing for one particular space of the hash table, there can be two the ways of resolving this collision can be divided into two categories. One is open addressing, another one is chaining. So, within the open addressing methods of linear probing and quadratic probing comes into the picture. In linear probing, we are looking for the next available slot for the key which has been already collided, and in the quadratic probing, instead of looking for the next available slot, we will be looking for the slots as per the square of the we can say the I, where I is if I is 1, then it could be +1 or -1, if I is 2, then it could be 4 +4 or -4. So, in this way we have distributed the collision resolution slots in case of quadratic probing. And as far as linear probing and quadratic probing are concerned, linear probing is actually we can say suffering from the primary clusters. The problem of primary clusters is being taken care in quadratic probing, while quadratic probing itself suffers from the problem of secondary clusters. Now, moving to the second technique, which is about chaining, or we can always also call it as the separate chain. As the name indicates, chaining, what are we going to do here is each position of the table is associated with a linked list or a chain of structure. So, let us say for example, we have table positions starting from 0 to 9. So, with the slots 0, we have one we can say chain or a linked list, or we can say with 2 we have another, with the third slot we have different. And what is going to be the content of the nodes of these linked list or chain of structures? So, structures, if we take it as chain of structures, or even if we take it as linked list, there are information fields of these chains. These information fields are going to store the keys which are actually colliding keys, and the reference to keys will be contained in the next field. So, let us recall the structure of a linked list. We have one data field and one list, one pointer field which is pointing towards the next structure or which is pointing towards the next node. So, information field of these chains will store keys, and the next the pointer field is going to store the pointer to the next node. So, this kind of chain or this kind of a linked list is associated with each and every position of the table. Also, a table of references or a table of pointers here is there, which is called a scatter table. Now, the best part with this table, which is kind of maintaining these linked list or maintaining these chain of structures, is this table can never go overflow, because linked list, when we talk about is going to be extended only upon the arrival of new keys. There is not kind of we can say allocation of the memory at the compile time, or allocation of the memory statically. So, dynamic memory allocation is always the concept which is associated with the linked list. So, this table can never overflow, because linked list will always be extended only upon the arrival of new keys. And as far as linked list is concerned, we can say this is kind of a method which is fast enough, but increasing the length of the list can significantly degrade the retrieval performance. If we want to retrieve a particular key which is, let us say, stored at the last node of the linked list, then it is going to take order of n time in order to retrieve or in order to look for that particular key. So, with the help of a figure, let us first of all try to understand what these how this chaining is actually going to work. So, here we have a table in which there are keys, some keys which are inserted. So, the first key is A of 5. Now, this A of 5, instead of putting that A of 5 on the slot 5, we are associating a chain with this fifth slot, and the first we can say the first node of this chain which is associated with the fifth slot is containing A of 5. Then comes A of 2. So, A of 2 again beginning of a new chain is starting with slot 2. Then there comes A3. So, A3 is only one node which is having its position as the third slot. So, A3 is there. Then comes B5. So, this B5 has to be kind of gone into the fifth slot, but fifth slot, imagine that already A5 is already there, or you can see that that list is already there. So, this B5 will be attached at the kind of end of that linked list, which was earlier having only one node, which was A5. So, now with the slot 5 you have two nodes, or a linked list containing two nodes, one is A5 and another one is B5. Please recall that this A5 and B5 are the keys which are actually, we can say, colliding keys. They both are competing for the slot number 5. So, instead of looking for any other slot of for this A5 and B for the colliding key which is coming later, let us say B5 here, we are not going to look for any other slot here in the table itself. Instead, we will be kind of incrementing the chain. Then after B5 we have A9. So, 9th slot has not begun yet with the linked list. So, one node linked list is attached to the 9th slot, which is A9 as of now. Then there is B2. So, the linked list which is at the second slot is extended to B2. Then we have B9. So, B9 again kind of A9 node, the node containing A9 will now point to the B9 because these are colliding keys, and then it is followed by C2. So, for C2 we already have the second slot, and the keys which are already kind of looking for the space over there are A2 and B2 available. So, again a collision. So, here collision means incrementing the list by one node. Whenever you have a colliding key, you are actually implementing, you are actually increasing the linked list of that particular slot by one, and that is why here, or this is how you are going to maintain the list of the colliding keys, or in the form of a linked list actually. So, now imagine that this A2, B2, C2, D2, E2, and there are so many keys which are attached to this second slot, and all these keys are now arranged in the form of a linked list, and we are looking for this, let us say, E2. So, in order to go to E2, this A2, B2, C2, D2, that means whole link has to be kind of searched. So, this is kind of a factor which is giving you a degradation of the performance. So, although this separate chaining is a fast method, but whenever the length of the list is in an increasing mode, it is going to affect the performance, retrieval performance basically severely. Now, the question comes up, this is the way we are doing chaining, or this is the way we are doing separate chaining. We can say, how can we improve the performance in case of large lengths, or the large lengths of the list, or the list which are having LS greater, or number of nodes is greater. So, in order to move the or in order to improve the performance, one idea could be we can maintain and order on all these lists. So, that means the elements which are to be inserted in list are to be inserted in an ordered manner. So, what is going to happen here? If there is an unsuccessful search, so for example, I am looking for a Y2, the key as Y2, and that Y2 is not available in the list which is attached with the slot 2. For these kind of unsuccessful search, an exhaustive search is not required in most of the cases, although Y2 is kind of, we can say it's a bad example, because this Y2 will come in the order it is going to be kind of at the last. But let us say for example, I am talking about G2 or F2 which is not available there. So, E and F are there, and then finally you have a P. So, if it is in the order, after checking the G and E, whenever we realizes or whenever your machine determines that there is not the key which you are looking for it not present, it will terminate the search. So, exhaustive search is not required in most of the cases. Another idea which is which can be implemented for this performance improvement is the using self organizing linked list. Now, what is this self organizing linked list? This is again a data structure which is going to be our upcoming topic. We will definitely be covering here. As of now, we can say these are the linked list, they will organize themselves in an ordered manner, so that the upcoming searches or the searching for a particular elements becomes very easier, and the less expensive as also. So, performance can be improved by either maintaining an ordered list or by using the self organizing linked list. These are the two ways in which we can improve the performance in case of large linked list associated with a particular slot. Moving further, if we can look into this chaining method, what is the first disadvantage which comes up in the mind? So, if we can see, it requires additional space for maintaining these pointers, and moreover your table is storing only pointers and each node requires one pointer field. So, if you can see in this figure, there are huge many pointers. There is a pointer in the slot, that scatter table I am talking about, which is starting from 2 and going towards the first node of the list, which is A2. Then there is a pointer from A2 to B2 and so on from B2 to C2. So, your table stores only pointers and each node also require one pointer. So, if we are going to calculate for n number of keys, n plus the size of the table pointers are required, which can be kind of huge if your L is if your n is very large. So, number of elements which are actually inserted into these hash tables, if it is going to be very large. So, for large n, maintaining a table or maintaining the pointers which are of maintaining the pointers and maintaining n plus t size pointers is actually a very demanding requirement, we can say. So, yes, because this storage of maintaining this additional burden of maintaining the pointers in case of separate chaining is something which one needs to kind of one needs to deal with when we talk about this. So, this is one of the we can say disadvantages of this chaining method. Now, there are different versions of this chaining method. They are kind of tweaked in some way or the other. So, one version of chaining is called Colescet hashing or Colescet chaining, which combines linear probing with chaining. So, that means this method is having chaining is definitely there, but at the first place the linear probing is being done. So, what is happening here is in this method, the first available position which is found for a key colliding with the another key, that is being kind of allotted to the colliding key, and the index of this position is stored with the key already in the table. So, wherever that we can say wherever that colliding key is going to be stored. So, for example, there is A2 being stored there at the slot number 2, then there comes B2, and with linear probing, let us say that B2 is having the slot number 5. So, along with A2, this slot number 5, which is the position of the colliding key B2, is to be kind of stored. So, what is the we can say advantage here? So, in this way, a sequential search down the table can be avoided by directly accessing the next element on the linked list. So, in the linked list, you have access to the next element, and then you can directly go there. Now, available, if the positions are available, they can be marked, let us say by -2, or it could be a marker indicating -1, designated as -1, which indicates the end of a chain. But what is the kind of characteristic of this particular method? That it requires more space for the table in addition to the space required for the key, because the next position at which the colliding key is going to be found is stored next to the original first key, I can say. So, the location of B2 is stored with A2. So, this method requires more space for the table. So, table kind of has to be increased in the space, while this was actually this is actually less than the chaining thing, because in chaining you are maintaining a complete chain, but the major factor here which is playing an important role is the table size. So, the table size limits the number of keys that can be hashed into the table. If you are not maintaining any extra chaining or something of that sort, then this is to be seen that whatever number of keys you are going to insert into your table, that number of keys is actually, you can say, limited by the table size, we can say. So, in order to understand this method of coalesced hashing, let us see this figure. So, this figure is showing here we have keys A5, A2 and A3, and we have put in this A2, A3 and A5 in their respective slots. Now, would it have been separate chaining? The different or the different linked list comprising of these nodes. So, 3 linked list comprising of A5, A2 and E3 would have been created, but here these are kind of, we can say, inserted into the table itself. Now, let us say there comes B5, and somehow this B5 is going to get the position, or this, let us say the B2, the key is B2, that is going to get the position 7. Then there is A9, that A9 is going to get the position 8, and there is B2. So, B2 is going to get position number 7, position number 9 is taken by B5 and 8 is taken by A9. Now, please you can see here that there is a link from A2 to B2, which indicates presence of this link is indicating that there is something which is which shares this particular space, we can say. Then there is a link from A5 to B5, and B5, as it was occupying the position of 9 and position of A9 basically, and if someone keeps on there, let us say there is a search which is looking for A9, then it will be immediately redirected to position number 8, and who is going to redirect it? It is the B5 who is going to kind of it is the position near to the B5 which is going to give this redirection, because there is a pointer from B5 to A9. So, the key which is getting collided with A2 is found at position number 7 by the virtue of that link. The key which is getting collided with A5 is going to get the position of 9, and the key which should have been at the position of 9 is available at position of 8. So, you just need to follow the links, and then when there are two more keys which are inserted, which are B9 and C2. So, C2 is being given position number 4, and this position number 4 is marked as the entry next to B2. So, there is a link from A2 to B2, then there is a link from B2 to C2. Similarly, I am talking about B9. So, A9 is available at 8, and from A9 there is a link to B9. So, in this way this kind of hashing is maintained, in which a colliding key is available, we can say is available in the last position of the table. So, whatever is the last position which is available, that position will be given to the colliding key. So, this is also kind of one method in which we can implement the chaining. So, chaining, if we talk about as the another method of collision resolution, so we have chaining there in the first and the simplest form is separate chaining. Then we have collision hashing or collision chaining. Now, we have just seen this example which is going to put the colliding key in the last available position of the screen, last available position of the table. Now, one more idea could be, or one more version of chaining is, can we actually maintain an overflow area separately. So, an overflow area separately is that overflow area is known as cellar, and that can be allocated to store the keys for which there is no room in the table T. So, the limitation of the previous method of hashing, that the table size is going to limit the number of keys which the table can contain, will be taken care in this way by maintaining an overflow area, by maintaining a cellar area that can be allocated to store the keys for which there is no room in the table. And this area should be implemented dynamically, maybe as a list of arrays or something of that sort, so that it should not kind of go in an go in a filled completely filled mode. So, that particular example which we have seen in our earlier method of chaining, here we are looking that with respect to the cellar, which is an overflow area, and in this figure which is that overflow area. So, that overflow area is shown by shown below the double line which is after the position number 9. So, the table size is 10. So, 0 to 9 are the slots of the table. Then we have 10, 11, 12, and this 10, 11, 12 are actually the overflow area. So, whatever the keys which are kind of coming colliding will be stored here in the cellar area, and obviously links are there as we have maintained in the previous method of hashing. So, here B2 is maintained at the position number 11, there is a link from A2 to B2. At the position number 12, B5 is maintained, because the policy which is being adopted by this method is the last available slot is given as the kind of we can say the next slot for the colliding key. So, after insertion of A5, A2 and A3 in the first figure, when there is B5 which is arriving, so that B5 is stored at the last position which is 12. Obviously, a link has to be maintained. Then there comes A5. So, A5 is A9. So, A9 is now kept at its original position. Then there comes B2. So, now B2 is kept at the last position which is available. So, 12th slot is already occupied by B5. Now, the next slot which is available is the 11th slot, and because of this B2 is stored over there, and obviously there is a chain or there is a link from A2 to B2. Now, other we can say elements are also stored in this manner, and this cellar is actually kind of implemented or kind of dynamically. So, that was this we can say figure which was having all collision hashing along with the cellar which is an overflow area. Now, the next solution to the collision problem is to store these colliding elements in the same position in the table. How can we do that? So, this can be achieved by associating a bucket with each address. So, here in hashing, what do we do actually? We determine the addresses by keys, and now we need to associate a bucket with each address. And what is this bucket? This bucket is nothing but a block of space which is large enough to store so many multiple items. But by using buckets, the problem of collision cannot be totally avoided, because this bucket is also having its kind of a space threshold, and if it is already full, then no new item can be inserted. So, bucket can also get in an overflow mode. But yes, we can say this is with the dynamic storage, but by incorporating the open addressing approach, the colliding item can be stored in the next bucket. So, within the buckets we can also have this hatching kind of thing. So, if it is the bucket is having an available slot when using the linear probing, and this we are going to kind of look for in this figure, which is giving you an idea of collision resolution with buckets and linear probing. So, each and every bucket, one bucket is associated with every address, or where we can say every slot of the table, and these buckets are maintained, we can say. And if the bucket gets overflow, then within the buckets this is going to be a linear probing thing. So, if you can see the second slot which is having A2, then there is colliding elements B2, and now let us say that bucket is full. If C2 is coming, that within the buckets a linear probing is being done, and whatever is the next slot available within the bucket, which is the third slot corresponding to the bucket, is filled by C2. So, the colliding items can also be stored in an overflow area, and in this case each bucket includes a field that indicates whether the search should be continued in this area or not. Now, this could be a simply yes or no marker also. So, if we can see here we have already we are almost done with our collision resolution techniques, in which we have covered our open addressing method, considering having linear probing and quadratic probing. Then we have also looked into some of the nitty gritties of bucket addressing, and also we have seen our chaining containing the separate chaining method and the method coalescent chaining or hashing along with the cellar. So, here is a list of references which is being used for the preparation of lecture. I will see you in the next lecture. More is to be covered in the topic of hashing. I will see you in the next lecture of hashing. Till then, take care. Goodbye.